Hello, this is Miss Moore, and today during chemistry we're going to continue our discussions on the gas law. Today we're going to talk about Gay-Lussac's law. Today's essential question: what is the relationship between the temperature and pressure of a gas? Please make sure you have your calculators handy. All right, we need to talk about something called STP. STP stands for standard temperature and pressure. Whenever you see the word STP or standard temperature or standard pressure or standard temperature and pressure, those are actually numbers, not just words. So standard temperature is 0 degrees Celsius, which is 273 K, and standard pressure is 1 atm. So if you're reading a word problem and it says the gas is at STP, that means the temperature is 0 degrees Celsius and the pressure is 1 atm. If you read a problem and it says the temperature, or it says at standard temperature, that means 0 degrees Celsius. And if the problem says at standard pressure, that means 1 atm. Okay, you need to know STP. You need to know that. All right, let's just get right into Gay-Lussac's law. So heating a gas will make it expand, which will increase the pressure. Okay, it can also increase the volume, but that would happen if the container it's in is able to change volume. It's stretchy. If you have something in a closed container that's not stretchy, instead of it expanding in volume, it will increase pressure. So gas molecules move faster when heat energy is added to them, causing them to strike with more force against the walls of their container. So the gas pressure increases. The other way goes if the pressure of a gas will decrease when a gas is cooled down. This is because molecules are moving slower. Okay, so Gay-Lussac's law. The pressure change of a gas caused by a change in temperature at constant volume. So this time the volume isn't changing. This is expressed as Gay-Lussac's law. So the pressure of a gas is directly proportional to the temperature on the Kelvin scale at constant volume. So just like with Charles' law, pressure and temperature are also directly proportional. If temperature increases, pressure increases. If temperature decreases, pressure decreases. Just to give you an application of Charles' law, of Gay-Lussac's law, if you've ever seen like one of those aerosol cans that says keep away from heat, well, that's because those aerosol cans cannot change volume, and if the gas molecules inside the aerosol can get too hot, start hitting the walls of the container too hard, you get too much pressure built up in there, bam, you get an explosion. Just a little aside there. Okay, so because the volume is held constant, it does not change. So when making a prediction about gas behavior using Gay-Lussac's law, we're going to use the exact same equation, P1 V1 over T1 equals P2 V2 over T2, but this time we get to ignore volume. There you go. All right, let's try a practice problem. Once again, write out your variables, possible variables. We have P1, V1, and T1, P2, V2, and T2. All right, let's read through the story and see if we can figure out what goes with what. So if a gas in a closed container is pressurized from 24 atmospheres to 35 atmospheres, so it looks like our original pressure is 24, and our new pressure is going to be 35. Okay, and its original temperature was 32 degrees Celsius. What would the final temperature be? All right, so now we know who's who. Let's fill this in. All right, our P1 is 24.0 atmospheres, which is atm. And our temperature 1 is 32 degrees Celsius. And our pressure 2 is 35 atmospheres, and we're trying to find our temperature 2. Okay, we got to go to our temperature. We need to change it to Kelvin. We do that by adding 32 to 273. which gives us a Kelvin temperature of 305. Okay, and now we need to plug stuff into the formula P1 V1 over T1 equals P2 V2 over T2. This time we get to ignore the volumes. So let's plug stuff in. We're going to have our P1 is 24 ATM divided by 305 Kelvin. And our P2 is 35 ATM. And our T2 is X. Cross multiply. And that gives us 24.0 ATM times X equals 305 K times 35.0 ATM. All right, so let's multiply. So now we have 24 ATM X equals 10675 K ATM. ATM. All right, and to get the X by itself, we'll divide both sides by 24 ATM. ATMs cross out, and that gives us, I got 444.7916 and so forth Kelvin. Okay, let's check ourselves to make sure. Our pressure started out from 24, ended up at 35, which means pressure increased, which means temperature should also increase. And we have 305 K and ended up with 445 K. So looks like we did it right. Okay, one more problem. This time, once again, why don't you hit pause, try to do it by yourself, then hit play and see how you did. Okay, once again, I'm going to make a list of my variables. I've got P1, V1, and T1, and P2, V2, and T2. All right, let me read through the story here. I have a gas in a closed container that has a pressure of 87 atmospheres at 32 degrees Celsius. So those go together. If the temperature is changed to 56 degrees Celsius, what will be the new pressure? All righty, so our pressure 1 is 87.0 atmospheres, and our temperature 1 is 32 degrees Celsius, which we need to change to Kelvin, which gives us 305 Kelvin. Let's see, our pressure 2 we don't know, and our temperature 2 is 56 degrees. Let's do that again. Is 56 degrees Celsius, which we need to change to Kelvin, and I got 329 Kelvin. All right, let's put this in the formula. P1 times V1 over T1 equals P2 times V2 over T2. And we get to ignore the V's this time. So we're going to have 87 ATM over 305 Kelvin equals, we don't know what, divided by 329 K. All right, so we're going to cross multiply, giving us 87.0 ATM times 329K equals 305K times X. All right, so now when we multiply, I came up with 28623 ATM K equals 305K times X. Get the X by itself. We need to divide both sides by K. No, by 305K, sorry. Giving us, I got 93.8459 and so forth K. Okay, let's do a quick check. Let's see, our pressure, we don't know. Our temperature increased from 1 to 2, which means our pressure should also increase. And we went from 87 to 93, so we must have done it right. All right, that's it for today. Have a good one.